All right, so welcome to lecture 5. We just took our first quiz. We'll get to that in a second. But yeah, just some quick reminders. Homework 4 is due on the 13th. There's not going to be a recitation in between. So that's why I made lecture 4 kind of on the lighter side. So homework 4 shouldn't be too bad. But it should cover material from lecture 4 and possibly from lecture 5. I'm not really sure. And then your midterm is next Wednesday. I know it's already there. It's already here. It's going to cover the material from lectures 1 all the way up to this lecture. Lecture 6, the one on Monday, we're going to start sequences and series because I wanted to make sure that like you guys are fully exposed to all of the wonder and majesty of sequences and series, because it does get a lot of fun and pretty crazy. So what we cover on Monday is not going to be on the midterm, but it is going to be on quiz 2. When is quiz 2? Do you guys know? It's on the 20th. So quiz 2 is going to have a good amount of stuff on there. There's a big gap between quiz 1 and quiz 2, just because the midterm is just in the middle. So please, once again, lectures 1 through 5 is going to be stuff you cover on the midterm. I'm sorry, is the stuff that's going to be on the midterm, which means the stuff on Monday, it's not going to be on the midterm, but you should still obviously like pay attention and obviously you'll cover that during the recitation on the 15th. All right. Tuesday's recitation should be covering the material from this lecture. And then the other half or so of the class will probably be like midterm review. Okay. Any questions about the homework 4 being due on Tuesday or the midterm on the 14th, the following Wednesday? No. All right. I apologize if my voice is a little hoarse today. We started the volleyball preseason started. I don't know if I told you guys this, but I'm a coach, so it's like I'm like losing my voice already because I'm like just screaming at them the whole day. So if I if I sound a little weird, that's why. Yeah. So yeah, let's talk about this quiz. What in the world happened?
Andrew
I need
said,
you guys to explain yourselves, please. What
no, Andrew
happened?
said he's in the waiting room. If you could just let him in.
What?
Andrew said he's in the waiting room.
Oh, all right. I don't know why this thing doesn't like ding dong when a person comes in. Usually it does that, but okay. Um, I need you guys to explain yourselves, please. Give you guys like a minute or two to respond, but you can respond in the chat. I don't care. Just tell me, please, what the heck happened on that first quiz. Did you guys even look? Did you guys see that I graded the quizzes?
Yeah.
Oh, okay.
Yeah.
I made a lot of dumb mistakes, but it was also like hard material.
I'm sorry, what?
I made a lot of dumb mistakes. Like I forgot to like switch back to the U sub. And I forgot to put C on like 2.
Okay,
but
there was no U sub on that quiz, so
no, because I substituted for you, and I just left you in my final answer.
there was no U sub on that quiz, so I shouldn't have seen any U's on there to start with. There was a trig sub question in which Gina told you guys to use trig sub, which some of you didn't use trig sub, so I don't know what happened there.
You gave partial credit for steps being shown, right?
Yep. Okay. So if you, I'm just letting you guys know, I was very lenient on this quiz. That the grades you got were lenient grade. Like a lot of them, like you guys just wrote down the problem and then just didn't even try it. I still can't believe people are still uploading JPEGs. Even when we were very clear on the directions, we told you guys multiple times to upload PDFs. Oh, but I'm still having issues with uploading PDF. Okay, so why didn't you tell us? So why didn't you tell us when you were uploading the first 2 homeworks that you could have practiced this with? You know, like why couldn't you tell us when we did the pretest? You know, it's crazy that you guys are still not listening, and it's honestly kind of disrespectful. Like some of the uploads, like I couldn't even. I had to like squint super hard, and like I couldn't zoom in enough. Like you guys aren't even taking your pictures correctly, you know? And yeah, it's like some of these submissions are like really, really disrespectful. I know that the professors, like if this was like a real class, they wouldn't even look at it. They would just give you the 0 for not uploading correctly, you know? And if this is kind of like the stuff that I have to keep expecting, I don't know, I might have to just start doing that too, where I just kind of, if you just don't even upload it correctly, or whatever, too bad, so sad, you take the 0. Like it's kind of getting to that point already. So this is gonna be the last warning. Please upload properly. What does that mean? Everything should be on the same PDF. There shouldn't be multiple uploads of a PDF. You shouldn't be uploading a JPEG, an HEIC, whatever, different type of file. You should be using a PDF converter or whatever, right? We've given you guys many instructions on this. Speaking of instructions, I don't know why I'm getting quizzes with like no work on them. You're just giving me answers. Are you kidding me? That's like Bush League. That's like, what are you doing? Like, why would you assume that I wouldn't want any work? It's also said in the directions to show sufficient work. Do you guys know what that means? That means you need to show your steps, your integration step. You're just showing me setup and an answer. What? You're just showing me answer. What? Like, how are you getting these answers? You guys know in the calc classes in college, they don't let you use calculators during quizzes, in-person quizzes, or I'm sorry, not in-person quizzes, but like during quizzes and exams and stuff. They need you need to be able to do the computations in your head. It's surprising that I'm getting a handful of students that don't know how to factor, that don't know how to solve for roots. What? If you're having trouble with that, then you should be back in like algebra. That's algebra stuff, guys. That's not calc stuff. You're supposed to be coming in here knowing how to do that stuff. Simple trig. Do you guys know how to do like sine of pi over 3 in your head? You need to be able to do that stuff, especially for today, right? We're gonna be talking about polar coordinates. And if you still don't know what a half angle formula is, oh my gosh, like what are you doing, right? So it's kind of like I'm getting people along with that skipping like 3/5 of the quiz. You're leaving 3 full questions blank. What? You guys, it's like some of you are just uploading. Oh my gosh, and like the uploads, like you're cutting off like parts of your work. What? Man, what is going on? And I just, that's why I need to hear from you guys. Like, what is happening? Like why aren't we asking for help? Why aren't we going to tutoring and asking for help during tutoring? Like, was this, I really hope if anything that this quiz was like sort of like an awakening for some of you. Because like scoring like 5% on this thing, that's not good. That's not a good thing, guys. And you shouldn't be thinking, oh, it's okay, he drops the lowest one. No, like you blew it on this first one. Like, what are you gonna do about it? You know? So I really hope you guys kind of like wake up a little bit here. There was like maybe 4 people that kind of did okay. 2 that did exceptionally, like 2 out of those 4 did exceptionally well, and 2 that were kind of like, all right, like it was okay, like they kind of understand what's going on. I can tell from the work that they're paying attention and, you know, kind of getting the stuff down. But dang, that is not the majority of the class. The rest of you guys, you know, it shows in your work that either one, you don't care and you're just like whatever, or 2, you're not paying attention during lectures, during recitation, and on top of all that, getting the help that you need. So I really need you guys to kind of like wake up a little bit here. Start asking for help, start coming to office hours, start asking like questions on like the group. Guys, I really don't know why it's kind of like pulling teeth with you guys. Like, take a picture of a problem, put it in our group me and be like, how do I start this? What I don't understand what is so difficult about that. And then I can be like, oh, you just got to do blah blah blah, and then there you go. Or hey John, or you send me an email, hey John, I'm kind of stuck on this part. You just take a quick snap. Those, I don't care if it's a PDF or a JPEG, whatever, right? You take a snapshot of your work, be like, I'm not really sure what I did wrong on this step or whatever. Is that like hard for you guys to do? Is that kind of like a difficult thing? Like so I really, once again, I'm opening up to you guys. What is it that we can do on our end that or that like, or what was it that was so difficult about this?
I mean, I just didn't finish the entire quiz on time. I feel like I could have been better on time.
How much time did she give
I
you for this quiz?
I skipped the differential question. I just didn't the one it was
Yeah, I don't get it. I gave you guys a
That's my
video
slow one.
on how to do those types of problems.
yeah, I even watched the video. I
And
just
most
didn't
of you
like
guys, please don't talk over me. Most of you guys skipped that number 4 question. That thing was worth 5 points. You couldn't at least separate the variables. You couldn't move all the y terms on one side, all the x terms to the other side. It was a simple algebra, right? Y prime is the same thing as dy over dx. No, so it's like I really don't. I don't know why so many people left that one blank. Adlin, what were you saying?
for the differential. So I think it was either number 4 or
Number 4.
I think it was number 4. I just didn't know how to how to go about doing that. Like I remember watching the video, and
I gave you guys step-by-step instructions, right?
Yeah.
Did you practice it or did you just watch the video?
no, I tried, like I did the homework. There was nothing on that in the homework though, but I watched the video, and I was
Okay,
trying to follow
so guys,
along.
watching videos, it's good. It'll help you guys a little bit, but the best way to like learn is to sit down with a pencil in hand and do the problem. Math is a stubborn subject. If you just watch a video and you're like, all right, I got it. No, that's high school level, right? And I've been telling you guys since day one that what you guys did in high school cannot transfer over into college. It's a different game. It's a different league. And you can't think that the way you studied in high school is going to transfer over nicely. A lot of like you're gonna find out I guess you guys found out, some of you found out already, that like it's very, very independent. It comes down to you actually doing the work properly. And I'm bolding and underlining that word properly. All right. Time management. All right, Andrew. All right. Like I get it. But I don't know. There was 5 problems. Some of them were multi-part. I think maybe the section with the integration might have taken you the longest, but we gave you 40 minutes. That's enough time for this quiz. You had plenty of time. One of the questions was like, is this a separable or a non-separable? And I can't believe people got that one wrong too, because like that was something, that's a quick question, like that's a quick answer. Like that one should take you like 10 seconds, right? Can you separate the variables or can you not separate the variables, right? Yeah, so I can't go into details about the quiz right now. Just remember someone needs to make it up. But if you want to come, I think I have someone come into my office hours today. So if you guys want to swing by 350, you can. I'll share my link or whatever in the chat. But yeah, guys, I really hope this was sort of a wake-up call for you guys to do something about it. I really hope you guys like kind of don't just like brush this off, you know. We got, yes, I do drop the lowest quiz, but like we got 2 more quizzes coming up, and I'm just letting you guys know it gets harder from here. Starting with today's lecture, it's gonna get crazy with the polar coordinates, especially if you've never seen it before. So yeah, all right, that was my little spiel. Anyone have any questions or comments or anything before we get into our lecture for today? No. All right. Okay, so what are we doing today? We're gonna finish off 9.4, which was logistic growth. We're gonna do like one more quick example, and I would definitely pay attention to this example because it's gonna look a lot like something on the midterm. And then we are gonna jump to chapter 11. Chapter 10 is, I believe, the like sequences and series stuff. So we're gonna come back to chapter 10 in a second, or after this lecture. And then, so we're just jumping to chapter 11. Chapter 11.1 or section 11.1 and 11.2, it talks about something called parametric functions or equations. I can't, unfortunately, get to it. I usually do, but like I said, I want to get to the sequence and the series stuff because that's the stuff that most people kind of struggle on. And I want to make sure you guys, you know, don't mess up when you get to that part in Calc 2. So I'm going to skip the parametric stuff. But I do want to talk about the polar stuff, which is 11.3 and 11.4, because that is also another section that's like, it gets a lot of people, it irks a lot of people. So we're gonna talk about that too. All right. So let's go right into 9.4. I believe I talked about this last class, but logistic growth. Right, we boiled it down to two equations. The first one being dp over dt is equal to kp, because it grows exponentially, but then has like this limiting factor of m minus p. Do you guys remember, what do m and k and p and t, what do these all stand for?
M is the carrying capacity, K is the logistic growth constant, and P is, so I think in this situation for what we were looking at is like kind of like the population size or whatever you want to refer to it as
And t is?
at the time.
Time, right? So P and T are kind of like duh, but K, yeah, we call it the growth constant. I guess you could also, we usually talk about logistic growth in the growth sense, but I guess you could flip it and say it's a decay constant as well. But yeah, I'm just gonna call it, you're always gonna hear me refer to it as the growth constant. M is what's called the carrying capacity. What does that even mean? What does carrying capacity mean again?
When the function, like starts to approach, it's like the maximum point that the function can maintain.
Right, so it's kind of like, it's actually like a value that the function will act asymptotically towards, right? It's gonna tend towards that carrying capacity, and then and it's kind of like almost like a roof, right? It's a value that as you go off to infinity, right, the function will approach. And which function are we talking about here? Are we talking about dp dt?
P.
We're talking about P, which is the second equation, right? The population function. P is the one that has that like S looking shape, right? And it approaches the carrying capacity, all that jazz, right? That's the one we're talking about. dp dt is not P of t. These are two different functions, right? dp dt is the rate at which the function changes, right? It's the derivative. So please make sure you understand the difference between the two. P of t was that weird looking formula. I looked at the view count. There was only 2 people that watched the video. So I guess 2 people were only interested in where the formula comes from. But anyways, it's m over 1 plus ae to the negative mkt. Once again, m and k are the carrying capacity and growth constant. A is it comes from the constant of integration, because in the video I used partial fractions, right? This is a separable differential equation, right? So I used partial fractions to actually integrate this thing, and you actually end up with equation number 2. So that's where equation number 2 comes from, and that's where that A comes from. We're gonna look at a problem. What's up, Adlin?
Is the carrying capacity, like, could you think of it as like a limit? Or is it more just like, does it never reach a like an actual limit, or does it just stop getting slower?
So on paper, the function should not technically touch the carrying capacity, because it is, like I said, it acts asymptotically towards it, right? It gets really, really super close, but never touches, right? But in real life, yeah, like the carrying capacity is like a value that you'd probably maybe fluctuate around, right? Like you might break the carrying capacity a little bit, but like it would always come back down to it,
But, like, you couldn't find the carrying
maybe stay
capacity.
under it. Adlin, can you not talk when I'm
Sorry, yeah.
when I'm answering your question too? So
Yeah.
just like, can you wait till I'm done, and then like you can like say your 2 cents? Okay. So so yeah, it's just it'll like fluctuate around the carrying capacity, but like it'll like maybe just like hover around that area in real life. Mathematically, no, it should never really touch. Go ahead.
So you wouldn't be able to get the carrying capacity by like trying to use limits.
No, you
Like,
would
like-
by the definition of a limit, right? Because a limit allows you to go really close to a value without touching it, right? That's the definition of a limit.
So you could find it like by using limits, but it's not a limit mathematically.
I mean, it's not really something you find. It's something that's like usually, given to you. It's something that is set in that certain scenario, right? And it's your function that gets really close to it. Does that make sense?
Yeah.
Okay.
Thank you.
Cool. Yep. So Let's look at a quick example. So let's say I have a logistically defined differential equation. I'm not even gonna write that down. I'm just gonna say given dp over dt is equal to p over 5, 1 minus p over 12. And this is something I just want to clarify because a lot of people kind of get confused on this part there in terms of like the definition of K or whatever. It really comes down to just how you define it within the problem. You know, some people would say that. Okay, well, all right. So first, let's talk about this example. What do you guys see here? What do you guys think is the value of M and K for this one? Or
K is 1/5 and M is 1.
M is 12.
Okay, so
Yeah.
some people are saying M is 12, some people are saying M is 1.
Wait,
and-
I'm pretty sure. Yeah, I'm pretty sure someone said M is 1.
well, okay, yes, someone did say M is 1.
I mean, like I agree that.
Oh,
M
you
is
agree that M is 1. Okay, all right. So M is 1, M is 12, K is 1/5. What do you guys think though? Like these are just guesses, but like can you like back these up? Like why do you think it's 1? Why do you think it's 12? You know, why do you think K is 1/5?
My guess is because dp/dt, it's the rate that population changes. You know you've hit your note. You know you're approaching the carrying capacity when this rate is getting to 0. If p approaches 12, that thing in the parentheses will get closer to 0.
Damn, Justin.
So
Damn, that was so well explained. You gotta speak up more, dude. Yes, guys, look at this, right? When our population approaches 12, as we get closer and closer to 12, right? Right? This whole value, this dp/dt will go to 0. You guys see that? Yeah. So yeah, I agree. I think M is equal to 12. I think our carrying capacity is 12. All right. Because for that sole reason. All right. So what about K then? Do we all just agree it's 1/5, or does someone want to say something else? Or
I'm too lazy to do the math, but I would set p over 5 equals kp, and then solve for k that way.
okay, all right, fine. Or you could just rewrite it as 1/5 p and just be like, oh wait, there's my KP, right? Some would argue that K is not 1/5. That the formula that I gave you guys, this first one, right? It's KP times M minus P. This technically doesn't fit this model, right? This doesn't look like M minus P, you know? You guys see that? How would I get it to look like something that, like, how would I get it to look like 12 minus P? Like, how would I get it to look like this? Because we know the carrying, we already said, we all agree that the carrying capacity is 12, right? How do I get it to become 12 minus P? What would I have to do?
I don't really know how to like phrase it, but basically, since P is over 12 inside the parentheses, you'd have to move like the 12 from the KP back into the parentheses.
The 12 from the KP back into the parentheses.
So basically, like you'd end up with, I think you'd end up with like P over 60 equals 12 minus P.
Yeah, yeah. Andrew, clever, very clever. So what Andrew did without knowing what he was doing, which is it's funny. I feel like it's a very engineering thing too, right? What he did was he actually factored out a 1/12. I don't know if you guys see that. In fact, I called it, this is a very special type of factoring. I know you guys when you guys learned factoring, you were like, oh, you can only do it when like they share the same factor, right? And like I can do that, right? Like that's the only time I factor. No, you can, like what I'd like to call force factor, right? Meaning I can factor out anything I want from any binomial, trinomial, whatever, right? So if I factor out a 1/12 from this, well, then that second term has to be a P, right? Because 1/12 times P is P over 12, which means if I factor out a 1/12 from 1, oh, it's going to look like 12 minus P with a 1/12 on the outside. You guys see how I did that? Yes, right? So with that existing P over 5 on the outside, some would argue that the growth rate is actually 1/60. You guys see that? So it's kind of a tricky question, I know. You know, some people would argue it's still 1/5. Some people would argue you got to account for the 112. I really don't think it matters. You know, it comes down to like how you like personally define your equation and all that stuff. So it's like I as a grader would accept either or, you know. So yeah. So I just wanted to clear that up because I had people in previous years kind of like ask me that question, like, wait, so is it 1/5 or is it 112? You know, I think if you go with 1/5, it's fine. It'll be okay. All right. So that wasn't the question though. Let's answer some real questions. I'm gonna skip the first part because it's basically saying, okay, so for this one, right? For this one, if I let t go to infinity, meaning like if I let time go on and on and on and on of p of t, what's that gonna equal? And why? We just talked about this.
It's gonna basically be 12.
Give me 12, right? As we let time go on and on and on, it's gonna hit its carrying capacity. Duh. All right, so that was an easy one. But if p of 0 is equal to 3, at what time is the population growing the fastest? So this is definitely something you guys need to know how to do. There's a lot of algebra involved. All right. So first and foremost, I don't have time. I just don't have time to do this. You're gonna find p of t. I'm just gonna tell you guys how to do this. Please do this on your own. You're gonna find p of t. You should know how to do this. You should refer to the last lecture notes to do this, right? Because I gave you an initial value, how much you started with, right? So you're gonna find p of t. And if it says growing the fastest, well, when does a logistic curve grow the fastest?
Biggest slope when it's the maximum derivative.
M over 2.
Right. So it is where it's growing the fastest. So that means on this graph, right? It's right in the middle. And we know what m is, right? So this is implying at p equals 6, not t equals 6, p equals 6. It means that when you have 6 things, that's when the amount of stuff you have grows the fastest. Yes. So how do we connect the dots here? How are we going to find, how are we going to figure out at what time the population grows the fastest?
You plug 6 in for the p equation and do algebra to solve for t.
Yep. Set p of t equal to 6 and solve for t. It's going to be some ugly ln decimally ugly answer, but in college level math, we like that. We like exact answers. So please don't give me like a rounded off truncated value because that's not the exact answer. Your answer should be some ln answer that's super ugly. Okay. So I'm going to do what lazy college professor lecturers do and just do ... and let you guys take care of that because I want to get to polar coordinates. Okay. But definitely know how to do this problem because it is going to come up on the midterm. You've been warned. All right, cool. So let's move on to chapter 11 already. Chapter 11 starts off, like I said, with parametric equations. We're going to skip that, but we're going to start with 11.3, which talks about something called polar coordinates. By show of hands, do you guys know, have you guys seen this before? Polar coordinates, this term.
Yeah.
Like, can you
Yeah.
guys use the participation thing and raise your hand, and so I can see how many of you have. Thank you. Okay, so it looks like 5 of you, 6 of you have. All right, so majority of you have seen polar coordinates before, so that's good. It's basically a different way to represent a given scenario. You like to sketch a function and things like that, right? You can sketch these out and you get some trippy looking things. These technically are still functions, but when you graph them, they like fail the vertical line test. But it's like, but by the way that they're defined, they still do fit the definition of function. I know it's a little confusing. Just know it's just a different way to sketch a function. I think that's the easiest way to kind of say this. You guys are used to what's called rectangular rectangular defined functions. That's like XY defined functions, right? It's just a different system. All right, and they use this a lot, especially in Calc 2 and 3. So please pay attention to this, okay? So it's essentially, it is a function, but your input is a theta value, an angle, right? You guys know, should know like how to plot angles and stuff on the coordinate plane. We are still playing on the XY plane. It's not like, it's not this, it's not theta and like there's an output. No, it's not defined like this. We are still playing on the XY plane. It's just how we get our points are different, okay? And when you input this theta value, it's gonna spit out what's called an R value. This is usually called a radial length, right? When you hear the word radial, you think of the word radius, right? Meaning that there's a center and you're going out a certain distance. So how do we plot these? Well, you're gonna go a certain amount of theta. Like I said, that's your input. And depending on your function, you're gonna go out a certain R length. And it gives you a point on the coordinate plane where you end up. So usually like they kind of denote it as like theta. Oh, wait, no, I don't know why they go the other way, but don't ask me, I don't know why. They usually define it as like R comma theta. Yes? I think a really nice way to illustrate this is think of like a cannon, right? How do we determine where the cannonball is going to end up? Well, first you have to determine what angle to fire at, right? Yeah. And then the second thing is how much gunpowder to put in or whatever, how much fuse or whatever, I don't know, whatever determines the explosion, right? I think it's gunpowder, right? So how much gunpowder you need for the cannonball to shoot out a certain amount. And wherever it ends up, that's kind of like, that's where it ends up. You know what I mean? Make sense? Yeah. So that's polar coordinates, like basically speaking. I'm gonna, you can go from rectangular to polar coordinates and back using some conversion factors. I'm gonna let Gina do some of those examples with you guys in recitation. Okay, I'm not gonna do the examples with you here just because we don't have time, but I am gonna give you the conversion factors because they're very, very, very important. The conversion factors, it actually comes from something you guys already know. Does this look familiar? You guys know what this is?
That's the circle equation.
It's the equation of a circle centered at the origin, right? So it's x squared plus y squared is equal to r squared. You use these or manipulate this essentially to get to from polar to rectangular or rectangular polar. Some other conversion factors, it's x equals r cos theta. This should look familiar, maybe, I don't know. But this comes from the unit circle, right? If you have the unit circle, right, and I draw a triangle, this x amount, this is the y amount, and this is your r. And if this is my theta, then it makes sense, right? Cosine is going to be x over r. You guys see that? Yes, maybe so, I don't know. All right, and then y is equal to r sine theta for the same reason. With these three conversion factors, you can go from polar to rectangular, rectangular to polar, right? Yes, makes sense? So I'm gonna do a quick example with you guys here. Did you guys get this down? Anyone still copying? I don't want to rush it. Anyone need anything from above? No? Okay. Let's pause example 2. So let's say I give you a polar function. Sometimes they denote it without the theta, sometimes they denote it with the theta, but once again, it's a function where your input is a theta and your output is a radial length, right? So that's why they use r of theta. You'll see this notation, right? Sometimes they just write the r, like similar, like, you know how you usually don't write like y of x, you know? But like sometimes they just do y. It's the same reason. So sometimes they'll do r of theta, sometimes they won't. But let's say I have r of theta is equal to I don't know, 2, let's say 2 sine theta. Right? And it makes sense. The thing on the right side, it should only have stuff with theta in it. right? Because once again, our input is a theta, it's gonna be a theta amount, and then our output is a radial length. So how do we figure out what this thing looks like? There's a couple of ways. Well, there's like, the first way is like a brute force way. Just plug in theta values and then see what comes up. Right? That's like a really, really long way. There's shortcut, there's shorter ways to figure it out. But if you, when in doubt, okay, when in doubt, theta it out. I don't know if that's catchy enough for you guys, but yeah, if you just like plug in theta values, right? So I don't know, give me an easy theta value to plug in.
Hi.
Okay. Well, I mean, like we don't want to go like out of order, so we'll get to pi, but let's do 0 first because 0 is easy, right? That means like you start on the positive x-axis. So if I plug in 0, well, what am I going to get? What sign of 0?
0.
Okay. So that means I have 0 times 2. So my radial length is 0. So if I were to plot this on the graph, my first point starts at the origin. You guys see that? Yeah. We'll eventually get to pi, but if you give me another easy theta value, like, I don't know, let's say like pi over 6. Do we know our sine of pi over 6? I hope so.
1/2. Oh, so I guess R would be 1.
It's 1/2. Yeah, so sine of pi over 6 is 1/2 times 2 is 1. So what does this mean? I go pi over 6 and I go out a distance of 1, which is about here. I'm like estimating, okay? I'm just roughly estimating. But let's say that was a pi over 6 and I go out a distance of 1 unit, right? What we're gonna find out if you keep doing this over and over and over is you're gonna start to generate. What does that look like?
A circle.
Yeah, you generate a circle with a diameter of 1. So, or another way you can think of this is a circle that was stretched out on the positive y axis. Make sense? Yeah. And you also are going to find out that it's sketched in a specific direction. And as you hit pi, it actually goes back to the origin and then just starts to retrace itself over and over and over and over and over and over again. So like they say that theta is in between pi and 0 to create one of these graphs, right? Because as soon as you dip over pi, it starts to retrace itself over and over and over and over. This is just one example. I'm not going to ask you guys to memorize, like, because like there are like parent polar functions, if you know what I mean. Like there are commonly used polar functions that you will come across in Calc 2, but I'm not going to ask you guys to memorize them. But there is going to be a midterm question that asks you to describe a polar graph function, and I'm just showing you one way to generate it. Okay. Any questions on this? No. The other way is to use your conversion factors. So this was way number 1. Way number 2 is to use your conversion factors. So if I have r is equal to 2 sine theta, well, if you remember, the conversion factors deal with like r squared and like r sine theta and things like that. So so how do we get r squared to appear in our whatchamacallit, in our equation? Well, you just use algebra, guys. So I'm going to multiply both sides by r. Let's see what happens here. Well, the left side becomes r squared. The right side becomes 2r sine theta. And if you guys remember, what did we say? The conversion factors. R squared is equal to x squared plus y squared. Y is equal to r sine theta. Do you guys see what we're going to do here? Starts with an S, ends with an substitution.
You're gonna substitute for r squared.
Yeah, you're gonna substitute these values because we understand x's and y's better than thetas and r's, right? That's the whole point of this. So I'm just gonna make a substitution. X squared plus y squared on the left side. On the right side, that r sine theta just becomes y. Right? If I subtract the 2y over, I can complete the square. I know you guys don't remember how to do that. Or some of you don't even know what that is. But you can complete this square and like I'm gonna dot this one because of time and actually get a formula for a circle I'm just gonna finish it off. How do you complete the square? You cut it in half and square it. So it's 2 divided by 2 is 1 and square. So you're gonna add 1 to both sides. And you get x squared plus y minus 1 squared is equal to 1. And that is a circle centered at 0, 1 with a radius of 1. Isn't that what we drew before? You guys see that? So yeah, you can use these conversion factors on points, or you can use these conversion factors on full functions to kind of go back and forth between rectangular and polar. All right, and hopefully Gina can do some more examples that you guys done in recitation. All right. Dang, like why is time going by so fast in this class? It's not fair. All right. So yeah, I'm gonna jump to. So by the way, did we do any calculus yet? Have we done any calculus with polar coordinates yet? No, we literally we're just talking about plotting and graphing them out. You can get some like crazier looking like polar graphs, right? You can get stuff with petals, right? You can get weird, ugly looking things. You get these things called cardioids. I call them butts because they look like butts. You can get things like limosons or like infinity symbols looking things, right? There's a bunch of different polar coordinates out there. I'm sorry, polar graphs out there that like are actually pretty applicable in real life, by the way. One quick example, do you guys know how mics work? Do you guys know what like a microphone? Like how we're doing this through Zoom and stuff, or how you make a phone call with your smartphone or singers, things like that. Well, the way microphones work, they receive in like sound waves, like and you can represent them through polar graphs, polar looking graphs, if you didn't know that. But anyways, yes, these do have their applications, believe it or not. All right, so I'm just gonna move on to 11.4 because that was an abridged version of 11.3. I could even I wanted to show you guys Desmos stuff, but like I have like no time. I was too busy yelling at you guys at the beginning of class. 11.4 is 11.4 now brings in the calc, right? Because we're in calc class, right? It now brings in the calc with polar coordinates. So it talks about area. It also talks about arc length. You guys know what arc length is? It's like how long a graph is, right? It's like measuring a graph, but I don't even have time to do arc length. So I'm just gonna focus on our area with polar coordinates. Because it's really cool. It uses the idea of integration that like you guys already know and applies it with polar coordinates. It's actually really, really cool, like how it works out, right? So the way it works, let's say I have a polar graph, right? I have some polar graph. The way this works, the idea is exactly the same as how we did area under a regular curve, right? A regular function, an f of x function. But how we come up with the area is different, right? How did we come up with an area under a curve with regular rectangular functions? What did we use?
Integral of top minus bottom.
Well, that's area between curves. I'm talking about area like in general. Like what did we have to do to get to find like
Riemann sums.
Huh?
Riemann sums.
Riemann sums. Do you guys remember Riemann sums? They took rectangles because rectangles are easy pieces that you can add up an infinite amount of times, right? However, we can't do that with this. We can't make rectangles from the origin, right? Instead, we have to use a different shape, or not a different shape, a different formula. I don't know if you guys can see that, but you guys learned something back in pre-calc. You learned something called the area of a sector. Do you guys remember sectors? A sector is like a fragment of like a circle, right? You start from the center of the circle, you go out to the edge, and you swing a certain amount of angle to get like a piece of the pie, right? That's what the area of a sector was. And you guys learned that the area of a sector was actually 1/2 r squared theta. I don't know if you guys remember that, but that was the formula for area of a sector. Now, it's really interesting because we don't want to find just a singular area of a sector, right? Similar to the for rectangular function, we don't want just one Riemann sum. We don't want just one sector. We want an infinite amount of sectors. Oops. We want like an infinite amount of sectors with super duper thin thetas, right? Okay, hopefully you'll see like this will make sense, right? With super duper thin thetas over a span of theta. Is this making sense? Is this connecting? Or does this kind of make sense? Right? So in essence, what we're doing is we're kind of like, the word I use is like sweep. We're like sweeping some amount of area and adding up those really, really infinitely small sectors, not Riemann sums. So we're going to use this to come up with the area of a polar graph, which is the integral, because we're adding up an infinite amount of sectors of, I'm going to pull out the 1/2 because the 1/2 is going to be on all of them, right? R squared, once again, this is our function. This is our f of theta, isn't it? Right? Instead of theta, we want infinitely small thetas. So we need d theta. That's it. That's the formula for area of the polar graph. Isn't that cool? Yeah, it's so cool, John. Yeah, I know, right? Math is so great. All right, and that's it. That's how you find the area of a polar curve, right? So a real quick example. I might have to make you guys do this on your own. Let's say page. Oh, by the way, polar coordinates starts on 11.3 starts on page 654. I'll put that up here. Page 654. So that's 11.3. 11.4 is like, I don't know, like 10 pages after that or something like that. I'm just gonna make one up. Here we go. So integral of, I don't know, 2 cos. Oh, I'm sorry. No. I'm doing the problem for you. Find the area of R equals 2 cos theta from 0 to let's say pi over 4. Oh, I forgot. I'm sorry. We're going from one theta value to the next theta value, right? You're sweeping a certain amount of theta. I forgot about my bounds. My bad. Sorry, I'm just because I'm rushing. I think that's it. Okay, yeah. So let's say I want to find the area of 2 cos theta from 0 to pi over 4. So I know you guys don't know what these graphs look like, but I'm just going to let you know. 2 cos theta, actually, can you guys guess? We know what 2 sine theta looks like, right? It's a circle that's been stretched out on the positive y-axis. What do you guys think 2 cos theta looks like? If you had to make a guess.
Does it look like a butt?
No, this isn't the butt one.
It's gonna be shifted on the x-axis rather than the y-axis.
Yeah. So instead of being stretched out on the positive x-axis, it's actually going to go, positive y-axis, it's going to go out positive x-axis. And the 2 tells you that it hits 2. Like this value is 2. Right? So there are like little tricks like that to help you memorize like the parent functions, but you guys don't have to worry about them now. You can worry about them later. The butt function, if you're interested, it's when you have a plus b, cos will make it expand out on the x, and it's like a equals b. The ratio between a and b is 1. So this is the cardioid. Did I spell it right? Cardioid. Yep. Cardioid, right? It's supposed to be like, it means like heart shaped. So this one would look like something like that, but it looks like a butt. All right. Anyways, so we're going back to the circle example, right? So don't worry about this. So how do I set this up? If I'm going from 0 to pi over 4, well, this one starts at 0, and pi over 4 is like somewhere like here. So you're actually like getting like this much of the circle. You guys see that? Does that kind of make sense? Maybe. All right. So let's get to the calculus of it all. If we're integrating this thing, my R function is 2 cos theta. So it goes 2 cos theta, but it needs to be R squared d theta from 0 to pi over 4. Easy peasy, right? Easy peasy, right? That's what you think.
Yeah.
That's what you think, right? Watch what happens. If I integrate this thing from 0 to pi over 4, I'm gonna pull out the 4. Oh, I forgot the 1/2. Whoops. So I get 1/2 times 4 on the outside because I'm just gonna pull out the 4. Then I get cos squared theta d theta. How do I integrate cos squared? Oh God. We don't know, right? How do I integrate cos squared? What the heck? We learned all those integration techniques. We should know everything by now, right?
Would it be reverse power rule?
No.
Use an identity.
No.
Leave the 1 minus.
Power rule. Is this a polynomial function? No.
You use one of those identities. It's like 1/2 times 1 plus.
Oh, snap, Justin. What are those called? It's not an identity. It's not a trig identity. It's a
I thought it was called an identity.
Half angle formula.
It's a half angle
Oh.
formula. I warned you guys. I warned you, right? In the beginning. If you don't know your half angle formulas, you can't integrate this stuff. We don't know what the integral of cosine squared is. We can't do it by normal means. We can't use power rule, can't use a trig rule, we can't use blah, 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 blah. All these rules, integration by parts, all these things that we learned. We need to know our half angle formulas to change this into a cosine with a power of 1, because that's the only way we're going to integrate this thing. So yeah, you got to use a half angle formula. It goes 1/2. Oh God. Plus, I know it. 1/2 plus 1/2 cosine 2 theta d theta. And once again, there's that theme of integration, right? What am I doing to my integral? I'm rewriting it, right? Remember we talked about that, right? That was the theme of chapter 7, rewriting your integrands. Is part of it. Rewriting your integral into something you can integrate. Because I know how to integrate 1/2, and I know how to integrate 1/2 cos 2 theta. Adlin, how do I integrate 1/2?
1/2. It's just 0. Oh, we know it's it'd be something.
Oh, my heart. Oh, you're killing me.
1/2
dude.
x.
Yeah, it'd be.
It's the
no,
power rule. I was trying to
No, yeah,
let
because the power
you
rule would
redeem
1/2.
yourself. God, man, goodness, I was like,
Would it just be x to the 1/2?
oh no, oh no.
It'd be
Oh,
1/2 theta.
oh man, Adlin, you're
Power
killing
of
me.
balance
dude.
of 0 to power of 4.
What's up?
It'd be well, obviously you separate the integral, and it'd be 1/2 theta.
Yeah, that's it. That's all I was looking for. It's 1/2
0 to
theta.
pi over 4.
Whew. Man, plus, how do I integrate 1/2 cos 2 theta? Oh my gosh. You guys do this yet?
Substitution.
No, come on. You don't need
So would
to.
that be sine 2 theta over 4?
Yeah. Right? If you start with a cosine, that means it came from a sine. If there's a 2 theta in there, that means you have to divide by 2 because a 2 pops out, right? You don't need u sub. You can use u sub, but we don't have the time, right? We integrated. We're going from 0 to pi over 4. This is algebra from here, okay? I shouldn't have to worry about this part, and yet it's the part that a lot of people screw up. If I plug in pi over 4, I get pi over 8 plus sine of 2 times pi over 4, so that's pi over 2, which is sine of pi over 2, which is 1. When I plug in 0, the whole thing just dies, right? If I plug in 0 for theta, first term goes away, sine of 0 is 0, so the second term goes away. So this is my answer. I'm not going to simplify this because I'm lazy as hell, but all right, fine, I'll simplify it. What is this? 2 over 8, so pi plus 2 over 8, but then times the full 2, so it's pi plus 2 plus pi over 4. That's our answer. Yes? Questions? No? John, is this as hard as the section's gonna get? No, it gets worse. There's more. There's another half to this section. I don't think I'll be able to get to it. I got 2 minutes left though. I'll introduce it and then I'll do the rest in the video. Because I just don't have time to go through it. But in this section, we talked about area within a polar coordinate, right? And if we kind of like transpose back to chapter, I think it was 6, when we were doing area between, I'm sorry, area under a curve. What did we do after we figured out how to find the area under a curve? What was like the next step up?
Finding the area between two curves.
So what do you guys think the next step up is here?
Finding the area
Two
between
polar
two polar
graphs.
functions.
Yeah, yeah, and this is like a very, very difficult. It's hard for a lot of people, because it's like super easy, right? Like, oh, if I have a polar graph, yeah, I just got to sweep a certain amount and then like, figure out like what the area is, right? But by plugging into the formula. But when you talk about area between two curves, there's a couple things you need to consider before just like kind of plugging it in. Area between two curves. I'll just tell you the formula from the get-go so that when you see it in the video, you won't be like confused. But the formula, in essence, is actually very similar to the formula for area between two curves. Do you guys remember what was the area between two curves? It was like top minus bottom. And then when we did area between two, when we did volume of like with washer method, what was that one? Do you guys remember that one?
Squared minus bottom squared.
It was outer squared minus inner squared. You guys remember that? It was like the outer like thing, and then you hollow out the inside with the inner one, right? I guess if you want to think of it as top squared minus bottom squared, fine. But I'm going to use outer minus inner because it's actually the same thing for polar graphs, right? It's actually the outer, I'm using it very loosely, squared minus the inner squared. There's still a 1/2. You're still sweeping from a θ1 to a θ2. It like it can loosely be defined as this. There are many different ways to find area between two, I forgot to put the word polar curves, but in essence, it kind of boils down to this idea right here. All right. The example I'm going to do in the video, it's I have a circle centered at the origin. So it's actually r equals 1. Think about it, right? It's like if r is equal to 1, that means the radial length will be 1. That means it's centered at the origin, right? The other one, is a cardioid. It's a bullet. It looks at 1 minus cos theta. So it's going to look something like this. And the question is going to go something like, find the area inside the circle, but outside the cardioid. I'll color it in. So it's the area inside the circle, but outside. Wait. Did I say this right? Inside the circle, but outside the cardioid. So what section is this like referring to here?
Side of the circle.
Huh?
The right side of the circle that isn't inside the cardioid.
Right. So it's like it's outside the cheeks. You guys see that? Right. So we got to understand like we got to know how to like extrapolate that information from the given problem. I don't have time to do this, but like I'll just tell you guys, you have to figure out where they intersect, and those will be the theta values you use to sweep. And then you do the outer, which is the circle minus essentially the cheeks of this thing. You guys see it? Or the B shape, beaver butt. Oren, what's up?
How do I join office hours?
Oh, you just tell me. Just tell me that you're coming to office hours.
Okay, I'll be coming today.
All right. Thanks, Oren. All right. So in this problem, you would do the blue. You would sweep the entire blue and then subtract away the cardioid from the intersection points. But I'll finish this one in the video. Finish in video. Okay. If anything, if I have more time, I'll maybe even do another one just in case. But yeah, that's it. That was your brief introduction to polar coordinates. Sorry, I ran a little over. Do we have any last minute questions before I let you guys go? I'm gonna say this just one more time, guys.